Okay. Okay. So first, thanks for setting this up. I will present the work that we did with Rosel. So it's called quasi-normal mode expansion of black hole perturbation. About the Keldysh approach. So you can find the preprint on this link. And this is sort of ongoing work also with Piotr, Valentin, Roselius, and Daniel. So I'm affiliated to Université de Bourgogne and Albert Einstein Institute. I put a star for my PhD advisors because I'm a PhD student. So I'll start with a quick introduction, present the compactified hyperboloidal approach that some of you already know. Then I'll present the recipe that we use to produce these QNM expansions. Then introduce some cases of study that we address in the paper. And then a very important point, I think, be the relation between pseudospectra and regularity. And I will end with some conclusions and quickly introduce six if I have time. Okay. So the context of QNMs, so you find it in astrophysical context, such as so coalescing black holes. So we have a phase right at the end, which corresponds to the ring down, where the black hole settles and relaxes. This phase, so it's described by a sum of damped oscillators, so these quasi-normal modes. But I don't want to give the impression that what we are going to discuss today only applies for this astrophysical context. It also applies for resonant cavities in optics also, which has also been introduced in separate papers. But right now, I'll focus on, in my cases of study, I'll focus on astrophysical context also. So first, let me introduce maybe the conservative case and what we are dealing with. So we are dealing with a linear equation, which has this form. So H is here the generator of the translations in time, infinitesimal generator of the translations in time. In the case of a conservative system, you'll be dealing with a self-adjoint operator, which acts so on a Hilbert space. And you will have there are eigenfunctions Vn, normalized eigenfunctions, as follows here. And they form an orthonormal basis of your Hilbert space and allow you to write the solution as a convergent series over the harmonics. So this is the normal case. So it means it commutes with its adjoint, and since it's self-adjoint, it commutes with itself. So this applies. And so the coefficient an is given by this scalar product. So I'll use this notation with a small g right here when I'm dealing with a scalar product. And so, yeah, so the linear equation, you have this and an initial condition for your time evolution. So, of course, several things that have already been addressed in the literature. So on the subject of completeness, so in the self-adjoint case, you can write any oscillation as a superposition of normal modes, whatever the potential really is. But in non-self-adjoint case, so non-normal, well, you don't have completeness for generic potentials. You don't benefit from these useful theorems that you know in the self-adjoint case. The aspect of spectral decomposition already is addressed somehow in the literature, but there's a need of a systematic approach, which is what we will present. We also have Keldysh expansion from the operator and it's a joint. And it's also been presented in some work with Casperin and Ramillo. And they try to highlight the structural role of the scalar product, but in the structure that in the structure that we will present, we don't need a scalar product. We'll work with the dual pairing. You will see later on. So general introduction, some definitions, I could say, on quasi-normal modes. So that I will abbreviate as QNMs. So you have a heuristic motivation to that, which is the resonant response under linear perturbation. So it's characterized by complex frequencies. And on the astrophysical interest, it probes the background space-time geometry. And the definition of QNMs in the context of this Lax-Phillips theory is really QNMs as poles of the meromorphic extension of the resolvent. And we really benefit from this Lax-Phillips thing. We'll build something on top of that. And so the way you to make the QNMs more clear, so it corresponds to this following wave equation. So in the tortoise coordinate, you can always write it this way. And so with a potential VL, which will depend on the type of the perturbation, on the type of black hole, and so on, with outgoing boundary conditions. So it wants to ingoing at the horizon, so it penetrates the horizon, but it goes at future null infinity. It's outgoing. So the first thing I'll just do is just a very simple change of variable to work with dimensionless quantities. I'll introduce t bar and x bar, just dividing by lambda, a scale, which will depend on the setting. This is presented in the paper, each case of study. So this is this. And the hyperboloidal approach, so you introduce a height function h and a compactification function j. So h corresponds in this picture right here. So it sort of lifts this sort of lifting function. And j allow you to so compactifies the inverse of j compactifies your interval, which goes from minus infinity to plus infinity. So this is the domain of x bar, which is infinite. But the domain of x is finite, so it goes from A to B, so that you're working with a finite region of space, but an infinite region of space-time. And here you have a picture of what this does in terms of Penrose diagram. So it's horizon penetrating, and it goes at it reaches psi plus. You also need to just one of two things about the killing vectors, so that you can interpret your frequencies. In particular, you have that lambda tau ticks at the same rate as t. And so the purpose of doing this is that you can cast your QNMs as really eigenvalues of a non-selfadjoint operator L. When L has some structure, it will look like this. We'll give more details next. I will first address the Hutton model, the Pochel-Teller. So in the Pochel-Teller case, so the equation that we've seen, and the potential is as follows. So V0 times hyperbolic secant square of x bar. So we make this following change of variables to define your compactified hyperbolic foliation. So this is really intuitive because hyperbolic cosine, log of the hyperbolic cosine will behave as x bar and minus x bar at infinity. And so this will give you, with this, you will work with an x that belongs in the interval -1, 1. Okay. Then, so among our recipe, we make a first order reduction. So we introduce the auxiliary field psi, which is just the time derivative of phi. And using this and writing the equation in the coordinate x and tau. So before we had an equation in terms of t bar and x bar. Now it's x and tau. The differential equations becomes this. Here you have a singular Sturm-Liouville operator, and here you have a term which is closely related to dissipations. So your differential equation becomes this with an initial condition, and by Fourier transform, you have this spectral problem, which keep appearing later on. You have an analytical result for Pochel-Teller, which is given by Gegenbauer polynomials. So this is a polynomial of order n, a polynomial of a variable x. And so you have also this, the eigenfunctions, the eigenvalues, or as follows. If you plot it in the complex plane so that it's easier to see, it corresponds to these two vertical lines. So one at minus square root of 3 over 2 and one at plus square root of 3 over 2. So this is just the view in the complex plane. Okay. So to sum up our recipe, so we have this hyperboloidal slicing. So we got from H height function, J allows you to come from the interval AB to minus infinity to plus infinity, and also takes the infinity into the boundary of your interval. We make a first order reduction. So the linear equation becomes this. You have a geometric interpretation in terms of outgoing null cones, and also an analytic one as built-in regularity conditions. And this singular Sturm-Liouville operator. So if you define functions p, w, q, gamma, and so on as function of j and h, so which characterize your hyperboloidal foliation, you can define your differential operators L1 and L2, and these are the bricks of your differential operator L. I'll put the color code so that you see broadly when they appear. So of course, I'm talking about the adjoint and non-self-adjointness and so on, but you need to provide a scalar product when you do that. So we have this scalar product. So it comes from the PRX. So it's missing a reference, but it appears several times in the presentation. So it comes as the energy of your scalar field, so Minkowski spacetime with a potential VL. And interestingly, so you can justify that the brick L2 right here is a dissipative term responsible for non-self-adjointness because you have this, well, delta or Dirac distributions. So since A and B are the boundaries of your interval, this justifies that this acts, this justifies talking about energy leaks at the boundaries A and B. And also, of course, you have the topic of instability of the QNMs, because they can be greatly perturbed upon a small perturbation of the potential. This really is an effect of non-normalness, because you don't benefit from the theorems that you have in the normal case. So now I present the recipe, so Keldysh. I just want to show you where you use the argument. So you start with your linear equation, so which is this one, the operator L that we have seen. Upon a Laplace transform and noting, so S equals I omega, you have after a Laplace transform, you will get this in the frequency domain, and acting on the resolvent, so which is defined this way on both sides, you get this. And Keldysh will appear to provide Keldysh theorem appears in our argument to provide an expression for this. So it goes as follows. So we consider a Fredholm operator. It acts, so it's a function of omega. So it goes from h to k. And you will define the transpose application of f as going from the dual of k to the dual of h. The spectral problem would correspond to this. So f of omega and f of omega n transpose. So there you see it discussed in terms of, the spectral problem of the transpose. And Keldysh theorem gives you an expansion of the resonant as follows, with h is a holomorphic function, and with this normalization condition. Yeah. And so this is really a normalization condition for alpha n. Now, if you use this in what I presented, so you will define f as L minus omega times identity. So your spectral problems are as follows. You can write the expression of the resonant of L this way. And then you replace the resultant by this, and through an inverse Laplace transform, you can provide this an asymptotic expression for u of tau x with this so normalization condition. And this is expressed in terms really not of a norm. This is expressed in terms of a dual pairing, really. Right. So this is many of these symbols. Yeah, and it's introduced. Did I introduce this? Okay. So this is not expressed in terms of a scalar product. You don't need one here. We're really using the structure of the dual and the transpose. Okay. So now I need to explain really what's the meaning of this wave sign here. So it's as follows. So you have a bounded domain omega on C, and you will define threshold R, which is the maximum of this omega. First, you write this. This is more or less a tautology, really. You have some of the expansion of the modes contained in your bounded domain omega, plus an error term. So sort of you stop your expansion, consider your truncated expansion, and the error term that you make when approximating u with this truncated expansion. And the meanings of this wave sign is exactly this. So it means that the error is smaller than the norm of the initial condition times a constant that doesn't depend on the initial condition, depends on L, on some parameter, but not on U0, times exponential of minus R tau. So in terms of notations, so that it's not, so that write something short and concise, I will work with this notation for the coefficients, so the amplitude coefficients, which is expressed in terms of the eigenfunctions of L. And it's convenient to work sometimes with this AN, especially in other contexts, such as the one in optics. So if you want to quantize your field in an optical cavity, you don't only want to read AN at null infinity. You might want to do that in an astrophysical context, but in a context of optics, you want to have the decomposition of your eigenfunctions. And so you might introduce AN. So the important thing is that really this calligraphic AN. So you can use this structure to compute it, but it's really independent. You can use really any norm, you will still get the same coefficients. But if you consider the an, little an, then it will depend on the norm that you use, meaning you can always renormalize V and multiply an by a constant. So this is basically the important thing here, because you have here a coefficient that depends on x, and here a coefficient that depends on the norm. Present one or two figures that tackle this. And a small notation that I introduced, so an with an infinite sign, is this coefficient evaluated at future null infinity to give really the coefficients of the QMN expansion on Stripless.
Sorry, I want to ask a question here. I'm not familiar with the Keldysh expansion, and I don't have an intuition for what you just showed. Like, what do you gain from it? It looks to me like you wrote the inversion of the eigenvalue problem in terms of some expansion with coefficients and poles, but what is the benefit of writing it like that, and where do you get those coefficients? Like, what is the intuition why you're doing this, if I may?
The intuition why I'm doing this because I want to study these QNM expansions. There are several aspects for that. So aspects of convergence of this QNM expansion, but here this is a structure which doesn't depend on the scalar product. It's a pure thing from functional analysis, and this how do I say that? This will give you a general framework that works that will describe the polynomial tails for if you have a space-time with polynomial tails. This will also work with higher dimensions, so not only one dimensions. And yeah, those are the main interests that I see for this using this Keldysh theorem. I don't know if this answers really the question, but I guess this will become more clear in the next slides.
Can I make a small comment?
Yeah, sure.
So I think that Jérémy explained very well the interest in the applications of using this, but at the level of the motivation why you look for that, actually what you are trying to do is something as close as possible as you would do in the self-adjoint case. So in the self-adjoint case, you would have a self-adjoint operator with eigenfunctions and eigenvalues, and then you have a recipe for calculating which are the coefficients, which is projecting. So you have a scalar product and you project. Now, so you have the guarantee that you have an expansion that converges, and in addition, a recipe for calculating the coefficients. So when you lose the self-adjointness, you lose the fact that the sum converge, so it makes sense, but also you lose the recipe for calculating the coefficients, the small an that he was commenting. So now you have different recipes for trying to construct the sum, and in particular the coefficients, and Marcus and Rodrigo did this very nice work in 2016, which they provide a recipe, a construction for calculating the coefficients. So here, what Jérémy is motivating is that when you don't have self-adjointness, you still can write the problem in a spectral manner, and you follow the same recipe that you would do in the self-adjoint case, except that you don't have to solve only one eigenvalue problem for the operator L, but you have to also to solve it for the transpose. And then instead of projecting with a scalar product, what you do is you project with the dual basis. You have the eigenfunctions and you have the dual eigenfunctions to that. You have the V and the alphas. So the V's are the V's are the eigenfunctions of the L, and the alphas are the eigenfunction of the transpose that lives in the dual. So then the alphas are distributions, if you want. So they are objects that act on the initial data and give you a number. So instead of making a projection using a scalar product, you use elements in the dual acting on the initial data to calculate the AN, the coefficients. Is that more? So it's somehow trying to mimic what you would do in the self-adjoint case, but now you don't have a scalar product. And what you do is, instead of that, you lift up the problem to the dual space using the transpose operator. Now you have two eigenvalue problems, and then you project, and then you recover the same structure. But now you don't have normalization. That's why, if you go to the next slide, I think, yes, the actual quantity that only really makes sense is the capital A, because this is independent of the scale of the normalization you would use for V's. This is what Marcus and Rodrigo use in their paper. So you can calculate if you want, you can fix a normalization for V. This will give you a coefficient small an, but the actual thing that is invariant is the product of both of them. So I would say, Anil, that in order to answer your question, the motivation for this is that if you can try to do like the Lax-Phillips approach, which is just acting with the green function on the initial data. But this is you do exactly the same but with a recipe of calculating the resolvent in terms of spectral tools. So you can the bottom line is that this is a spectral recipe for Lax-Phillips construction.
Yes, no, this is beautiful. Thank you. I got it now. I mean, the dual, that makes sense. You construct somehow something like a scalar product, even though you don't have it, because it's, no, I got it. Okay, thank you.
Yeah, thanks, Luis. Okay, so then I wanted to give a small illustration of what that might look like if I compute, say, the error term, and I define my my bounded domain as the biggest domain that contains the fundamental mode. So just to give an example of what that means in terms of sorry, giving a more explicit expression for E. So for instance, here I'm writing the expression for the error that you make when you include only one mode into your expansion, and that would look like this. And it means you have the error term, which is bounded by some constant times exponential of minus the imaginary part of the first overturn times tau. But I'll get back to that if we need to. Okay. So now, so we'll present our cases of study, and most of our main results for these simulations. So I want to mention that, of course, I presented Pochel-Taylor, which corresponded to this hyperboloidal slicing. You have expressions for several other cases of study. So the Schwarzschild case, you find it in also in the literature. It looks like this. So it's simple enough so that I can write it on the slides. You notice that this time
the literature means Rodrigo.
Yeah.
Rodrigo's work.
Yeah, it's in some of the slides. And so it cancels quadratically at 0, at sigma equals 0. So this time, so Pochel-Taylor was the toy model, so it's Minkowski, and Schwarzschild is so the black hole case. So sigma equals 0 corresponds to photon infinity, and sigma equals 1 corresponds to the black hole event horizon. So this P cancels quadratically at sigma equals 0, and this will give us a branch cut, which you will see later on in the spectrum. So of course there are several cases of study. I'm giving here an example of a table that I made to see these potentials. I will just mention quickly because the expressions are really long. So the Schwarzschild de Sitter, you can find it in these two references. P vanish linearly at the event horizon and the cosmological horizon. So I will sort of assimilate cosmological horizon to future infinity in my slides, but really it's this boundary of the interval. And it's expressed in terms of several surface gravities. And the Schwarzschild ADS case presented in these two references. So in this case, you impose reflexive Dirichlet boundary conditions at the ADS boundary. And this acts like a box that confines the field, and you only get dissipations at the event horizon. This will, yeah, I mean, we have, this is explained more detailed in the preprint. Okay. So just a few elements on the numerical methods. So we use Chebyshev, the Chebyshev interpolation scheme. We work with the Chebyshev-Lobato grid to include these endpoints. And we have a polynomial interpolation. We will discretize vector phi and psi and u that will appear as a column vector with n+1 entries. So at the matrix level, the size of the entities at the numerical level, so it depends on the size of the grid size n. There are n+1 points on this grid. And we also have numerical instability. So we need to work with arbitrary precision numerics in order to get a spectrum that, in order to avoid spectral instabilities in our spectrum. So we'll work with a very high very small decimal precision. So a few parameters that are involved in our simulations. So put them in red. So n is the size of our Chebyshev-Lobato grid that samples the variable x. The decimal precision, which is set to a very high value. Then the parameter called tolerance, which is a parameter for the ODE solver. It controls more or less the precision of the ODE solver. Yeah, which I will use here as a black box. I don't want to get into the details of the way ODE solvers are optimized in the code, and I'm working with Julia, so a programmation language. So for our work, we fixed an initial data for all these simulations, and I would consider on several panels our cases of study. So Pochel-Taylor, Schwarzschild de Sitter, the cosmological constant, which is 0.07, Schwarzschild, and the Schwarzschild ADS. So to show maybe an example of time evolution, I will show you a video. These are the waveforms at photonal infinity. So at one endpoint of your Chebyshev-Lobato grid, and you look at you apply the method of lines, and you look at the evolution of the field at this point of this collocation point of the grid. So yeah, if I ready. Yeah, okay. So if I show you the evolution in time of the field. So I will show here the x-axis is little x, and the y-axis is the field, and I'll let the field evolve in the time tau. So you see it quickly settles and becomes flat. So this is actually the fundamental mode. The fundamental mode for Special-Taylor is just a constant function of x. And so it becomes flat and then oscillates. And the waveform that you see is, so looking at the endpoint here of this correlation of the Chebyshev-Lobato grid. So if I showed the early times of this, yeah, so that's it. So you see our initial condition, and then you can sort of assess how the outgoing boundary conditions are implemented. Okay. So yeah, that was to give really the evolution and see the interval x. So this was for Pochel-Taylor, and you can generate similar things for these or cases of study. Okay. So these are the spectra of our cases of study. So you have Pochel-Taylor here, Schwarzschild de Sitter here, Schwarzschild and Schwarzschild ADS. There are some interesting things right there. So of course, for Schwarzschild, you see you have a branch cut, so a continuous part of the spectrum. These are modes that don't converge with the grid size. So you can increase the grid size as much as you want. You're not going to get modes that eigenvalues that converge. But those which are not on this on the imaginary axis do converge, and the algebraic special mode also. Here you have so in the de Sitter case this time you have some modes on the imaginary axis. These are convergent modes, de Sitter modes. In the Schwarzschild ADS case, in order to implement the boundary conditions, we make a change of variables, and we end up with a generalized eigenvalue problem. And this is a detail of a detail that is addressed in the preprint, and I will not really elaborate on this. So now a very rudimentary convergent test for this 4 cases of study. So what you see in general for Pochel-Taylor, Schwarzschild de Sitter, and Schwarzschild ADS is that B eigenvalues align until some threshold on the imaginary axis, and then they start to split. And this gives you a way to roughly evaluate the convergence of your spectra. This is more or less easy for these 3 cases of study. You see it converges. This allows you to observe in particular the tiny oscillations that you see for Schwarzschild de Sitter for the high overtones. It's interesting that in the Schwarzschild case, it's much harder to assess the convergence of the modes. That the convergence is much lower than the other cases. It's sort of contaminated by the branch cut. So in our simulation, we will consider here a few. It's 300 QNMs. Here it's about 200. Here it's about 70. Here it's about 30 or 25 QNMs. And this would require, of course, a more rigorous test of the convergence of the QNMs, but this gives you a first assessment of that. So now use these solvers, these ODE solvers tools that I have with Julia, the arbitrary precision and so on, to compare the solution, the time domain solution, and the spectral approach, so the Keldysh QNM expansion, and I compare the waveform at future null infinity with the QNM expansion that I get. So there are several things to say here. So the first one is that it seems to be a very good fit for surely for late times, but even very early. In particular, in the Pochel-Taylor case, you see that you are able to fit the waveform even at the very, very early times. In the Schwarzschild de Sitter case, you are able to fit before the maximum of the waveform, and the Schwarzschild ADS case also. In the Schwarzschild case, it's more complicated. The assessment of what modes have converged or not is harder. And you see that, well, because of the branch cut, which contaminates this. And you see that the blue, so in blue, you have this, the solution from the ODE solver, the time domain solution. And in orange, you have the QNM expansion with the spectral approach. And you see that you have a good fit from well 5 to maybe 20, and after that you start to see a difference between these two because you have a polynomial tail due to the presence of the branch cut, and which justifies this mismatch at late times. Okay, so for Pochel-Taylor, Schwarzschild, de Sitter, and Schwarzschild, I plot this at photon null infinity. For the ADS case, I plot it at the event horizon because at the ADS boundary, the field is 0. So this justifies why I do that. Now I'm just showing the difference between the last blue and the orange curves, so that you see that this is limited actually by the accuracy, the tolerance of the ODE solver. So it's and you see at early times the difference is big, and then it starts to reach the precision of the ODE solver. And so by adding more and more overtones, I can fit very early times. For Pochel-Taylor, it's obvious. It's very hard to see how this works in the Schwarzschild case. Yeah, in particular because we have tails. Now, what I'm showing is the capital 8, the coefficients of this QNM expansion. So the one you see in orange. This is the QNM expansion of the field out on Schwarzschild+. And I'm showing the amplitude coefficients of this QNM expansion. So for Pochel-Taylor, they get very, very, very low, and they start to decrease. For Schwarzschild de Sitter, they increase. They have some convexity, which we can speculate whether this will eventually decrease or not. For Schwarzschild ADS also it increases. And so these results highly depend on the initial condition that you consider. I define clearly early in my presentation what is the initial condition that I'm considering. And this is presenting to you so the coefficients and also convergence tests of these coefficients. So this is the log of the modulus of these amplitude coefficients of the QNM expansion on Cypress. In the Schwarzschild case, once again, it's complicated. It's hard to assess the convergence. We can be confident that the first one have converged, but when you get to very high modes, there's a mismatch. But there seems to be a trend. It seems to be decreasing after a while. And this is sort of with our simulations, we can speculate that if you increase the grid size high enough, these coefficients will go to 0, and that would correspond to the growth rate, which appears in the Ansorg and Macedo paper, which there's a whole conjecture on that, which we can discuss afterward if you want. So now I want to insist on how we recover the tails, the polynomial tails. So what you see here in the is a plot of the waveform. Here you have the eigenvalues, and here you have a log view of the first panel. So there's a color code here, so orange for the branch cut and blue for QNMs. And what you're able to do with that is to separate the contribution of the tails and with QNMs. So there's an important thing here because you're not supposed with this Keldysh scheme to be able to recover the eigenvalues. These the polynomial tail, you're not supposed to be able to recover these behavior, but you can if you add or if you compute the Keldysh expansion over the eigenvalues in yellow, you get the curve in yellow. If you do it for the one in blue, you get the curve in blue. And at first, we didn't really understand why that was the case, because it's supposed to be excluded from the integration contour when you take the inverse Laplace transform. But we got a more clear understanding of why this happens. I will show it to you in the next slide. So, and here I want to insist on the fact that we recover the price law. Yeah, we cover so the price law. So it has to be a polynomial behavior tau to the minus L plus minus L minus 1. Okay, so now I will justify why.
Can I just make a quick question? I mean, it can be very briefly, just understand. So you recover the tail by filtering all these QNMs. I understood correctly that you do not get the tail from the Keldysh expansion. Is this the case?
Yeah, no, you get it from the Keldysh expansion over the modes in orange.
You get directly from the Keldysh expansion.
Exactly, yeah.
Okay, cool.
Same methodology, yeah, exactly. Same thing. Instead of just summing over the modes in blue of things that have converged, you sum over the branch cut eigenvalues which have not converged, and you recover the tail this way.
Okay, cool.
Yeah. Perhaps can I make a comment? Sorry.
Comment. We have about like 5 to 10 minutes to wrap up. So
yeah, maybe
a longer discussion, but I don't want to.
Yeah, okay. I think it's a good idea. Yeah. So quickly, I want to comment on the fact that it's not really surprising that you recover the tail because, well, if you assume you can diagonalize your matrix L that way, you can show really by it's a really basic linear algebra that the formal solution of your equation, which you write it as by exponentiating L. Upon injecting this expression inside L in this relation, you can show that the Keldysh expansion over all the eigenvalues of your matrix is precisely the formal solution that you get from the evolution operator. So this is quite intuitive if you use matrices. If you get used to matrices, you see that really it seems really obvious. But what we're really doing is we are finding the eigenvalues that are responsible for the tails in the formal solution of the ODE, which is exponentiating L and multiplying it by the initial condition U0. Yeah, so this this is just a picture to show that if you consider more and more overtones, you can fit the waveform very early. So it goes from red to blue. So red is just the Keldysh expansion with only the fundamental mode. And in blue, it's Keldysh expansion with 200 overtones. And you see that you can fit very early. And actually, the one in dark blue, you don't see it on this picture because it has an amplitude coefficient which is really, really small. So we can describe the very early times of this of the waveform by adding enough overtones. Okay, this I want to get to regularity aspect. So to say a few words about pseudospectra, so I will skip this for the moment. Maybe we can go back to this if it's needed in the discussion. So you know the pseudospectrum has been introduced in particular in the PRX and introduced in my references a few slides ago. So this answers the question of where the eigenvalues of L migrate upon a perturbation delta L of L of norm epsilon. So what are the set of complex numbers, which are actual eigenvalues of a perturbed L plus delta L operator. So you have a perturbative approach, which says exactly that. So we have lambdas in complex plane, which are eigenvalues of L plus delta L. And you also have an approach through the norm of the resolvent. And these two are exactly the same thing. So by evaluating the resolvent at some point in the complex plane, you evaluate your pseudospectrum. So in the self-adjoint case, what you see is really circles centered around your eigenvalues with horizontal lines when you get far away from the real axis. And this is really intuitive because it means really the eigenvalues can't get very far. And so it's really intuitive in terms of stability of your eigenvalues. In the non-self-adjoint case, you don't have such figures. So this is the kind of the energy pseudospectrum that you get from Pochel-Teller. But there is a huge there is a huge issue with this pseudospectrum, and this issue is that it doesn't converge with the grid size n. So this means even if you present this, you cannot trust the values that you read on this pseudospectrum. They all go to, so this is the log of epsilon, so they go to minus infinity. Everything goes to 0. And this is really coherent with this idea that any point in the complex plane, that in the way we define QNMs as eigenvalues of the non-selfadjoint operator, we need to provide regularity conditions on your space of functions, because otherwise any eigenvalues in a complex plane can be a QNM. And so this is really coherent because it means that if it diverges, that if any epsilon over here goes to 0, this really makes sense with this notion that you need to address regularity issues to define QNMs. So really quickly, so you have HP QNMs, so where addressed. So Warning was the first to read this in 2015. Then you had a paper from on structural aspects of the ADS spectrum. HP QNMs are defined as eigenvalues of the HP regular operator, which is defined that way. So restrict your operator L on Sobolev HP regular functions. And if you do that, then the QNMs form a finite set below some threshold in the imaginary axis. So here A is a constant, kappa is the surface gravity, and P is the exponent of your HP. And if you do that, and define HP scalar product that way, you find that you have a pseudo spectrum that converges in bounds. So I will give a few pictures of that next. And the idea is that for HP, so here it's H4, for instance, all the points below the imaginary part 4 have converged. All these the norm of the resolvent evaluated at this point have converged. So let me give you a picture. So first thing that you see is that the spectrum becomes flat. You can increase P. So this is H8, H9, 10, 11, 12, 14, 13, and so on. And eventually what you find is that they form circles centered on your eigenvalues. And this is a pseudo spectrum that has converged. So I'll show you a convergence test, but you see how that increased the regularity because your eigenvalues are forming circles around your eigenvalues and vertical lines. So this is exactly the same picture, except I fixed the color bar to show you that there was a strong gradient on my figure, and so you couldn't see these control lines, but they very early they start to form circles and vertical control lines, indicative of increased enhanced stability. Yeah, okay, that way. And so the claim about the convergence of the pseudo spectrum is that say here it's H10, all the point below imaginary part equal to 10 have converged. So this is what I will do right now. So in the 2 minutes I have left. So I will sample the complex plane this way. So I will put some points. And I will evaluate the pseudo spectrum at these values in the complex plane as a function of the grid size to show that this has converged. And I don't get the same issue that you had with the energy pseudo spectrum, which doesn't converge. So if I do that, so here I'm showing for the H1 norm. So you will get only the first one that has converged. So only the first one is flat. Then H2, you see the first two are flat lines. It's 3, 4, 5, 6, 7, 8, 9, 10. And yeah, so what I'm showing you is really the log of the norm of the resolvent as a function of the grid size. Okay. Sobolev HP norms also have the interest of giving you a sort of qualitative control over your overtones to sort of control these little a n, which is the quantity that depends on your norm, and you can have a sort of control over this by choosing your scalar product, and this will give you a sort of qualitative control over these coefficients. Okay, so I will skip this. Let me present my conclusions roughly. So you have a unique expansion at future null infinity. We've introduced a scheme that generalizes the previous QNM expansions. This works with higher dimensions. This works, you can recover tails with that. It is an agnostic in the sense that you don't need a scalar product. Dual pairing is fine. And this is what you use instead. You recover polynomial tails. You can verify the price law. You can assess the contribution of the high overtones. I've presented the HP pseudospectra, which converges according to the criterion that you find in 1X paper. And Lassie also explained how doing Keldysh over all the eigenvalues is related to the dynamics of the evolution operator, and so to the formal solution of the ODE solution. Okay, so thanks for your attention. I think you have questions, so thank you.
Thanks.